This is the 2023 higher paper for triple physics, year 11, equation sheet. Into the first question then, which is on radioactivity. So some straightforward answers here. The risk, they can damage cells, they can cause mutations while handling. How do we limit that? How do we control that measure? We limit the exposure time. So, or we can shield when not in use. So that's how we can limit our exposure there. So we're given an absorber. So it's either going to be paper, aluminium, and lead, because that's what stops each of those alpha, beta, and gamma radiations. And we're asked to work out, explain why the data shows that there's no alpha particles. It's because when you put paper there, it doesn't actually drop. So you can see that the background rate is 256 with no absorber. We put paper there and it's still 256. So there's no alpha present, but it does drop with aluminium and lead, which brings us to this question here. Explain how there's beta and gamma. So you can say the count rate drops at aluminium and the count rate drops again at lead. State one cause of background radiation. So you've got a bunch of things to choose from. So radon from rocks, we've got cosmic rays, we've got food and drink. That's all natural. Nuclear power stations, medical uses, they're all man-made radiation, but it's all comes under background radiation anyway. State how the results in the table should be corrected for background. You just subtract the background radiation from all other radiations. So when you measure without an absorber, you're going to get a count rate. And then if you subtract that from all other rates, that gives you the true value then for that element. Question 2 then. We've got a car weighing 10,000 newtons. And we've got gravity worth 10 newtons per kilogram. So I'm just going to stick that into the formula to give us a mass of 1,000 kilograms. So if I've got my weight and I've got my gravitational field strength there. The resultant force is always the leftover force. So I'm going to take the 2,000 away from the 5,000. So you can see it's accelerating this way. Okay, so there's a bigger force this way than this way. 2,000 due to drag there, so I've got a resultant of 3,000 newtons. And now I can use that to calculate the acceleration, because that's going to be the resultant force over the mass, which we worked out there. So it's that 3,000 over 1,000 gives me 3 meters per second. Don't forget to put squared on, because that's acceleration. Meters per second is a velocity. Meters per second squared is an acceleration. Explain how resultant force as it changes as it speeds up. So it's going to decrease because air resistance or drag or friction, whichever one you want to use, also increases for 2 marks. State how this change in resultant force affects the acceleration of the car. Well, the acceleration is going to decrease because every time you get close to terminal velocity where the forces are balanced, the acceleration is 0. So it's always going to decrease the acceleration, even though it's still getting faster. It's getting faster, less each second, which is why it's a rate, and which is why it's meters per second squared. We've got an energy now, joules, 72,000 joules, and we've got 15 meters. So we've got work done, which is joules distance, and we can work out our force. Our force is 4,800 newtons there for 2 marks. On to the next question then, question 3. We're dealing with the sun, similar size to our sun. It's 4.37 light years. So how long is it going to take? It's going to take 4.37 years. Okay, so tricky one. It's only worth 1 mark, but we need to be clear on that. Even though 4.37 light years a distance, it's going to take 4.37 years to arrive. Explain in terms of named forces why it's currently stable. So you're going to have gravity, the inward force, is equal to gas pressure. So they're balanced, equal and opposite there. Explain in terms of named forces the next stage. So the next stage is going to be a not a supergiant because it's a small star. It's going to be a red giant. So the gas pressure is going to increase. It's going to get bigger. And it's going to get, so the forces are not balanced this time. And we're only dealing with forces. We don't have to comment on any of the reactions until we get to this bit. Hydrogen is going to get used up in the fusion. So it's used to produce helium now. So that's what happens at that stage. On to a triple question here then. Triple question, we're dealing with an absorption spectra. So you can see that these lines, and we're given for 6 marks, we're asked to explain firstly what the dark lines are from this bit and explain which elements are present. Now we're given a table to give us the wavelengths of these different types of elements, each has a barcode. But I'm just going to run through this very quickly. Not going to take too much time on this. In fact, you can pause this, read it, and everything there. Every good point is worth a mark. So the big ones here is that you need to know that the light is absorbed by the star's atmosphere. And each element then identifying them, you're going to identify from what is there. So you can see helium, you need to have a line at 447 and you need to have a line at 502. If you've got lines there, then helium's going to be present and you can read all that there, okay? So I'm going to go on to the next question. So we're dealing with Hooke's law now, spring. We've given a bunch of data. So we're given mass, force, and extensions. So we're looking for, state the mass of the greatest uncertainty. So the greatest uncertainty is going to be the biggest range. So I can see at 200, I've got 8.9 and 9.3, whereas the others are quite close, like 13.6, 13.7, 18.2, 18.5, range of 3. There's quite a big range there. So I've said 200 grams. And then I think we use that their range. So we put the maximum minus the minimum over 2. We're given the equation right by there. So that I'm going to use that and it comes out with an answer of 0.2. Suggest how students could adapt the apparatus to reduce. Well, just put the ruler closer to the spring because that's going to reduce human error for reading it. You can see that the spring is all the way over here. The ruler's there. If the spring was by here, you'd have a much better reading. Calculate the mean extension for each force mass. Plot a graph of force against mean time and then determine the gradient is how you could determine the mean value from all. So I've drawn quickly a little sketch of a graph that you'd expect to see. You can see if it follows Hooke's law, then the force is going to be proportional to the extension, which is x, and then the point at which it curves is going to be the elastic limit. That's where it no longer obeys Hooke's law. These are the two equations you'll find from the front of the book that link these. So just be mindful of that as well, okay? But this, yeah, quite a hard question because use all of the results to determine, well, it's all to do with the mean there. So calculate the mean and then plot that graph and then determine that gradient because that gradient is going to give you the K value. Oops, didn't mean to do that. The K value on that spring constant. So spring constant is just how springy the spring is really. How does it want to stretch or does it not want to stretch? And the higher the spring constant, the less stretchy it is because it requires more force to move a distance. Okay, this is double and a bit of triple because you do come across these equations in double. However, this links with the triple, and what we got to know is everything on this side equals everything on this side. So let's have a look what's going on. So I've got uranium, we're told, has got 92 protons in its nucleus, and then neutrons there. So we need to add those up because a nucleon number, the mass number they would use in chemistry, is going to be the number of protons plus neutrons. So that gives me 235. And then obviously the proton number is just the proton number there, the number of protons. Then they're giving me a neutron. That's going to equal now cesium. I'm going to get, again, the same method. So 55 plus 85 to give me 140, and then 55 on bottom, plus my rubidium. And again, it tells you what it's going to become. Okay, so if you're not sure of these, it's all in the question. So it's kind of a word equation there. So rubidium, 9237, plus your 4 neutrons, because you need 4 neutrons now. I don't know if it actually tells us that. No, it doesn't. In order to balance 140 plus 92 plus something gives me 235. That something is going to be 4. 4 times 1 is going to take us to that. And then because the neutrons have no protons, it's going to be 0 on the bottom. So 55 plus 37 gives me 92. Okay, 4 times 0 is nothing. Explain, so 4 marks available for that. Explain the purpose of a moderator is to slow down fast-moving neutrons. Need to be captured by the nucleus. Explain how the rate of reaction can be increased in a nuclear reactor. So raise the control rods because they absorb any excess neutrons that's flying about. So the fewer neutrons are absorbed, therefore more are able to go on and cause fission. And now we come on to, this is a double question. So a lot of that to do with triple there. But now this bit is double because I'm given 2 half-lives. I've got rubidium is 4 seconds and I've got cesium is 64 seconds. At time 0, the mass of cesium present is this. The same mass of rubidium is also present. So calculate the mass of cesium after 64 seconds. So the half-life of cesium is 64. So after 64 seconds, just 1 half-life, so just half in that. That's all I'm doing there, 65,536 grams. That's why it's only worth 1 mark. When we come to calculate how many half-lives, you could do it in one of those tables, but because I know there's 64 seconds and there's, let's have a calculate, and it's got a half-life of 4 seconds for rubidium, I can just divide 4 into 64 and it's going to give me 16 half-lives. All right, so that's just an easier way. You could do it with the table, but it's just going to take you a little bit longer. I am using the table now, though. After 32 seconds, 512 grams. So I'm starting with 512, and remains calculate the mass of rubidium after 64 seconds. So I need to get that rubidium. So it says after 32 seconds. So after 32 seconds there, that remains. So I'm going to keep going with my half-life. Every half-life is 4 seconds, isn't it? Let me just check that. Yeah, it's 4 seconds for rubidium. So it gets down eventually after 64 seconds to 2. I'm halving each time on the bottom. I guess the biggest mistake that can be made here is that you would start with 0 there, as you've been taught, but this is a problem solver after 32 seconds. So after 32 seconds, the mass is that, okay? There is another way you could do it mathematically, but I'm not going to go into that in the video, so you can come and see me about that if you need. Initially, the ratio of mass cesium is 1:1. Explain how this ratio changes in time. So because I've got, after 64 seconds, I've got a mass of 2 there, and after the same amount of time there, I've got this mass. I'm just dividing one mass into the other. So after 64 seconds of cesium, it was that. After 64 seconds, rubidium is that. How many times does that go into that? And that gives me a ratio of 1 to that. So again, a numeracy question there. Okay, a couple more questions to go there. I think there's 2. No, this is the last question, which there's 3 pages. Okay, stopping distances and break-in and thinking distances. Let's have a look. So thinking distance, if the tire tread is worn, it's not going to affect the time it takes you to think about it. So that's going to be the same, but it is going to increase your braking distance and therefore overall stopping distance. So it's going to have an impact. It's going to increase the impact speed, okay? When it comes to this question, then we're giving a little bit more data. So we're saying if for every, didn't want to do that. Every 10 kilometers per hour equals 2.8. And it wants us to look at 60 kilometers per hour, which is over here. So I've circled it in blue, all right? So my ratio there, so I'm going to times 2.8 by 6 because there's 6 tens in 60. So that's going to come out with 16.8. So that's my initial speed, all right? Because it tells me there for every 10 kilometers, the meters per second is 2.8, and we're doing it 60 kilometers per hour. So now I'm going to go and look at my table for thinking distance. So the thinking distance is 25. I've highlighted it in orange. You can see the thinking distance is the dark region. So I got 1, 2, 3, 4, 5 squares of 5, which is 25. And while I'm here, to go back, I can see now that the braking distance is 1, 2, 3, 4 boxes. So that's going to be 20. And we can see that 45 minus 25 is going to be 20. So I've filled those out. So I've got 25 is my thinking distance, braking distance is 20. Overall stopping distance then is both added up, so 25 plus 20. That's a nice little 4 marks there. Thinking time. So I'm going to use my thinking distance over the time. Over the speed. So I've got my thinking distance of 25, my speed of 16.8. I'm using this equation from the front page. So you could say speed equals distance over time, or you can say time equals, so you rearrange that as you need to. Then we come on to a triple question then using SUVAT. Now it's only going to slow down when the brake's applied, so it's not thinking distance we're not going to deal with. So only the 20 for braking distance we're going to be using. I can see that my initial speed is 16.8. And then we're given the equation to use anyway, so 2ax. I'm looking for my acceleration, so I'm going to be rearranging this to give me my deceleration of 7.06. You can put a minus there. It doesn't matter whether you put the minus or not, because it says deceleration, but you will find, because you've got a 0 on here, which is the final speed is going to be 0, right? Because when it's stopped, that's when it's 0. So when everything comes over to this side, it becomes a negative. Explaining in terms of Newton's first law, this is a nice one because the seat belts produce an unbalanced force on occupants. This prevents them moving forward at constant speed. So that's linked with Newton's first law there. We can link that with inertia. An object will remain at rest, or uniform motion, and this is the uniform motion bit. So while if the car's stopping and you're not, you're still going, that seat belt then is going to produce that unbalanced force on you to hold you back. In terms of Newton's third law then, the third law, car is going to produce a force on the obstacle, and the obstacle is going to produce equal and opposite force on the car for 2 marks. And that is Newton's third law, isn't it? Object A exerts force on object B. The obstacle, object B, produces equal and opposite force back on object A. Explaining in terms of Newton's second law then, so with all the laws coming up here, this is F equals ma. How can we link that to safety? Well, crumple zones increase the distance or the time, right, of the collision. Therefore, it's going to reduce the force, which reduces deceleration, acceleration on the occupant. So I would go with force there rather than deceleration. But it is linked with F equals ma because the mass is going to stay the same. If you can bring the acceleration down, you can bring the force down. And the way to bring acceleration down is a change in speed over time, which is linked with distance over time to get to that reduced speed. Then the last question for 3 marks. This is a little bit of a common sense one, but you are going to agree with this statement because we can get a decrease in accidents, which should reduce the severity of the collision there for 3 marks. And that was the end of the paper. So hopefully you've got something from this. And if you've got any questions, please come in and see me.